So in this session, what we'll be doing is we'll be studying a number of transducers. It's not possible for us to be uh, investing a lot of time in studying all the different types of transducers available there. There are hundreds and thousands of them. So what I'm going to do is in this session, I'll be listing some of the transducers that are again somewhat much more important, and I'll be rushing through them so that we can wrap up this unit and we can move on further in this course. So, starting with, we have the force displacement measurement. We have studied the potentiometer, the resistance strain gauge, the LVDT, the capacitive transducers. So the first two are actually resistance based transducers. You have then the inductance transducer, and then you have a capacitance transducer. So all these different types of transducers can be used, whether passive or active, can be used for measurement of force, displacement, pressure, etc. Then we have the temperature-based temperature measurements. In that, we have studied the resistance thermometers, we have studied the thermistors. Then you also have a thermocouple. So from Seebeck effect, you already know that if two dissimilar metals are joined together and heated, the temperature difference arising at two different junctions. One will be the hot junction and another one will be a cold junction. The difference in temperature at these 2 points will cause and will produce a voltage, and this voltage will actually be proportional to the difference in temperature. So this particular effect, what we can do is that we can actually insert one junction in a medium whose temperature we want to check. It should be a hot medium, and its temperature will will be different with respect to the cold junction. So the proportional amount of voltage that will be generated will help us determine what will be the value of temperature. Then you also have digital temperature sensors. In these devices, what we can have is that we'll be having an analog device for measurement of temperature that can be converted into an equivalent digital output using ADCs. Yeah, the flow measurement. In case of flow measurement, we have already seen the hot wire anemometer. We have seen how a varying flow rate can be determined using a hot wire anemometer. We have ultrasonic flow meters as well. So the principle in this case is that uh, and an ultrasonic wave is actually propagated through a fluid medium, or any sound wave is propagated through a fluid medium. Its velocity will change, and that velocity will actually change with the proportional to the change in the velocity of the fluid. Right. So this particular principle, in this particular principle, what we do is that we actually provide short bursts of ultrasonic pulses or sinusoidal pulses, sinusoidal sound waves through a fluid medium whose velocity we want to change. We can note down the variation in the propagation of this ultrasonic wave or the sound wave whose frequency will naturally change with change in velocity. This change in frequency can be measured, and that will give us an equivalent amount of change in the velocity of the fluid rates. Another type of device for measurement of flow is electromagnetic flow measurement devices. In this case, what we do is instead of using ultrasonic waves, we now use electromagnetic waves. The principle is similar to that of a Faraday's electromagnetic induction principle. In this particular case, our fluid will be electrically conducting. Fine, we'll be having an electrically conducting fluid. That means, and we'll be placing this electrically conducting fluid in a magnetic field. So we have an electrically conducting fluid that's actually moving, and it's placed in a magnetic field. So we know by magnetic principles, by electromagnetic induction principles, and EMF will be induced in this fluid. Fine. E is equal to BLV. We know B, we know L, we know E, so we can measure the velocity with which this fluid is moving. Fine. Similarly, you have the laser Doppler anemometer. So using the Doppler effect, in which we actually propagate light waves through the fluid medium, and these light waves will be scattered through this object, through this fluid medium, depending upon and its frequency will change. So we can measure the frequency of this electromagnetic wave, uh, uh, changing electromagnetic wave, changing frequency of this electromagnetic wave, that's actually light here, through this particular object, that will actually be proportional to the velocity with which the fluid is actually moving. So using these different principles, we can actually measure the fluid or the flow rate in case of velocity or the flow rate in case of fluids. Then you have devices known as magnetostrictive transducers. So there are some materials like iron or nickel whose permeability changes with application of stress. Fine. Now this can actually be a positive change or a negative change depending upon whether this is a compression or a tension. And this effect is known as Villari effect. This change in permeability of magnetic materials uh, under stress is known as Villari effect, and these devices are known as magnetostrictive or magnetoelastic materials. So this property can be actually utilized for measurement of stress, strain in different transducers. This will actually cause a variation in induction. This as permeability changes, inductance will change, and that inductance can be measured using any AC bridge, and uh, it will generate an equivalent amount of voltage. That equivalent amount of voltage proportional to the change in inductance, proportional to the change in permeability, owing to the property of stress being applied on these particular type of materials, will help us note the stress being applied, will actually give us a measure of the stress being applied. So magnetostrictive transducers in short will help us in measurement of stress due to the property of these materials, which is changing permeability. Yes. Now you need to also measure liquid levels. So we are actually focusing on different types of measurements: temperature, flow, light, displacement, pressure, stress, etc. So you have liquid level measurements. We can have two different types of liquid level measurements. One can be a direct method, and another one can be an indirect method. In case of direct methods, what we have is that there are methods in which the liquid level can be directly indicated by means of a simple mechanical type of device. It will be actually a flow operated device being operated electrically, and this uh, float, that will be actually a floating device that can actually be here as the primary transducer. That's actually the primary sensing element that will convert the liquid level measurement into a suitable displacement. That can be either a linear displacement or a rotary displacement. And attached with this will be a secondary type of transducer that can be either a potentiometer or an LVDT, where that will actually be sensing that displacement of the fluid. And using this property, we can see that whatever will be the proportional variation in resistance or inductance, that will give us the indication about the change in liquid levels. This is actually the direct method here. We have a mm, we have a float connected to a wiper, or in this will be a linear device, or in case of a rotary device like this, and this wiper will be moving across along this potentiometer now. So you have, this is a primary transducer here. This will be the secondary transducer. This can be either a potentiometer or an LVDT. That will be used for measurement of displacement. The liquid will actually transform first into, so the mechanical displacement of the liquid will be transformed first into mechanical displacement of this wiper. That will be transformed into electrical change in resistance or inductance. That will be actually cause of generation of voltage. That measured voltage will give us the level with which this liquid is rising or decreasing. So this is the direct method. You have another method, and that will be the indirect method. So in case of indirect method, what we have is the hydro. So we have actually the measurement of liquid levels through the in this case through pressure instead of displacement. In which direct methods we have directly measuring the displacement. In case of indirect method, we will be actually measuring the pressure and through that pressure measurement we'll be measuring the change in liquid level. So we know that hydrostatic pressure caused by a liquid is directly proportional to the height of the liquid column that we have studied in the secondary school. P is equal to rho gh, and therefore what we can do is we can use a device or a transducer to measure pressure. So pressure gauge will be installed at the bottom or on the side of the tank. That will be used for measurement of pressure, and that pressure measurement will be proportional to change in the liquid level of this particular change in height rather. That will actually be the liquid level. So any rise and fall of liquid level will cause an increase or decrease in the hydrostatic pressure here. So that pressure measurement that will give us the change in that pressure measurement can help us determine the liquid level. So this is a hydrostatic pressure type device. You have a pressure gauge installed at this very point that will be used for measurement of pressure, and or you can have different type of mechanism. It's a dielectric liquid level gauge. So in this case, capacitive capacitance will be actually a factor by which we can measure change. Variable capacitance will actually be used for measurement of pressure, and that will give us the rise and fall in this particular device. Fine. So the electric medium between these two plates will change, and that will change the capacitance, and depending on the height, depending on the level of fall or rise in this particular medium. Fine. We have the ultrasonic level gauges. They are again used for measurement of levels. So sound waves are actually directed towards the free surface of the liquid that we need to actually whose level actually we need to measure. So what we have in this case is that we have a transmitter that will be generating ultrasonic waves. So this device can be installed on top of this vessel in which the liquid is contained, and as soon as ultrasonic waves radiate back from the liquid, they will be received by the receiver. So the time taken by this ultrasonic wave to be transmitted and received back by the receiver will actually give us the if the liquid level is low, that means more time will be taken. If the liquid level is high, that will means lesser time will be taken for the propagation of ultrasonic receiving and transmission of this ultrasonic waves. So this particular application helps us determine the level of this liquid surface. We are particularly installing this on top of the vessel so that we can measure the distance the ultrasonic wave has to travel. That will actually give us the height of the liquid. Fine. So this particular method, although it's applicable, it's quite expensive. You can understand it that we are for simple measurement of liquid levels we are using ultrasonic waves. We have to generate them and then transmit them and then receive them. So the actual instrumentation is expensive and it will require a high degree of experience and skill in operation. But the advantage with this is that level measurement for different types of liquids and solid substances is possible using ultrasonic level gauges. Fine. So another type of device is a light measurement device, and that's a photoconductive cell. So under light, we have studied photoconductive cells previously also. That these are actually devices that produce variable resistance. They are actually variable resistance transducers. We study them under variable resistance transducers. They can be used for measurement of light. So these photoconductive cells will be much smaller. They will be more sensitive and more rugged than a photoimmersive type. So the photoconductive cells, its electrical conductivity will change with the light intensity it receives, and so these photoconductive cells, they are made up of a thin coating of selenium, germanium, or lead sulfide. That's all the technical details of. So you have selenium, germanium to produce. Fine. So we have to maintain a ratio of 5:1 and 8:1 for lead sulfide and selenium respectively, as compared with their resistance in the dark. These are some properties that you need to note. So, in short, photoconductive cells produce an equivalent amount of voltage depending upon the light it receives. Fine, its electrical conductivity basically changes with the light it receives. And it's a passive device, it's not an active device, so it will require an external source of power. And so these semiconductor devices operate on the principle that light gives enough energy to the valence band electrons to raise them to the conduction band. Fine. So the more the so that means when light strikes the photoconductive cell, its energy requirement for the electrons to move from valence band electrons to the conduction band decreases. That means even at it will be able to conduct in this conductivity increases with increase in light intensity. That means it becomes a better conductor, lesser amount of energy is required. So the resistance of this particular device reduces with increase in light. So that property can be used for major. That change in resistance can give us an equivalent proportion. Can be measured using any bridge, and that will give us an equivalent proportion of light falling on these devices. So there are still many other types of transducers available there. You have the microphones, you have carbon microphones, you have uh, microphones itself. They are capacitive based, they are electromagnetic based, so they transmit audio signals, they receive audio signals and generate electrical energy, or and vice versa. So that means you can measure sound, you can measure light, you can measure pressure, you can measure force, displacement, stress, strain, uh, extra, all these uh, non-electrical quantities using transducers by converting them by converting that non-electrical energy into an electrical energy form, and that helps us. That electrical energy is easily measurable using different types of devices that we have, bridges in particular, and that so these transducers are quite uh, inexpensive as compared to mechanical devices, and they are less they also have better efficiency, better reliability as compared to mechanical devices. So that's all for this unit. So in the next session we'll be starting with the unit 3, that is instrumentation amplifiers.